Cool, thanks. All right, guys. So this is Euclid again. We're going back to proposition 1.6 and revisiting some of these other ones that didn't get recorded earlier. So let's get started. So proposition 1.6 is about. I always start with the blue. Proposition 1.6 is about isosceles triangles as we know them today, but of course they probably didn't have this name for it back then. So essentially, what we're trying to prove today in here is that if you have a triangle where two of the angles are equal, then the two corresponding sides of these angles are also equal. So I'll draw the diagram. So if you let ABC be a triangle, right? So I'll draw the triangle here. I'm going to draw with straight lines. So there we go. So ABC is a triangle. Right. So if the angle ABC and angle ACB are equal, then the sides AB is equal to AC. And so you've got these two angles being equal, and we want to prove that the two adjacent sides are also equal. So proof, I'm going to try and fit this on one board. Hopefully I succeed. So suppose AB is not equal to AC. It's not equal to AC. Then one is greater than the other, and we can assume one is, well, let's assume that AB is greater than AC. AB is greater than AC. So I'm also following Dan here as much as I can to try to not use symbols to try to keep true to the original. But sometimes I may still revert back if I run out of space. But I'll try my best to stick with just words. And so what we're going to do here is we're going to use proposition 1.3 to cut off a length on AC, such that, or actually it's cut off a length on AB, right, a point here such that ABD, oh, I did it again, let's erase, such that BD is equal to DC, and we're going to construct this line here. All right, so I'll just draw it in first, right? So I'm going to let change back. So I'm going to let D be a point on AB, right, such that ABD is equal to AC. And we know we can do this from proposition 1.3 that allows us to cut off from a point along a line any given length. Right, so BD is equal to A, so just mark that, right? These two are equal. And so now we're going to use postulate 1 to draw a line from D to C. I'm not going to write that in, I'm just going to mark that in a diagram. And so we're going to use proposition 1.4, which tells us about, I guess, in modern language, congruent triangles, right? So now, since DB is equal wow, I always click on the wrong buttons. I gotta click it twice, right? Equal to AC, right? And the angle ABC is equal to angle ACB, ACB, and BC is a common side, right? We can conclude that the triangles DBC is equal to the triangle ACB, right? So this is proposition 1.4. Okay, so what have we concluded here, right? So DBC is a smaller triangle, right, in the diagram, and ACB is the bigger triangle in the diagram. One's contained in the other, and since they're equal, this is telling you that D must be equal to A, and so AB is equal to AC, right? So, or another way of seeing it is that you've got two congruent triangles, then AB. Well, no, actually, the triangles are superimposed on top of each other, so that means that D is equal to A, so the line AB is equal to AC. Okay. Any questions? Cool. So I'm gonna try and see if this will work. So Dan tells me if I walk over here to use the next board, the orb should also. Oh yeah, there we go. Nice. Okay. So if there are no questions, I'm gonna keep moving on and talk about the next proposition. So proposition 1.7. So this is talking about if you have a line and you have, say, a triangle constructed on one side of the line with two intersecting lines, then if you construct another triangle with the same endpoints on the line, with the same lengths, then this is necessarily the same triangle, right? So you can't have different triangles with the same side lengths sharing one side, so to speak. But of course, this, I think in the text, they don't use the language of triangles, but I think it would be slightly clearer if they just express this in terms of triangles. So I'm going to do, I'll write down what it says in Euclid, slightly paraphrased because I think as stated in there, it's kind of confusing the way it's written. So given a line, so I'm gonna draw the diagram at the same time as well. Hopefully I don't mess up too much with the line tool. So given a line AP, so this is the line that we've got. I won't label it just yet. Well, actually I will label it, sorry. AB. And two other lines which intersect, whose endpoints are also on the line. On the first line, I'll draw these in. So let's just use A and B as the endpoints. And yeah, we've just got two lines like this. They intersect at C, say C, and if the endpoints in A and B. So the statement is that it is impossible to construct two lines with the same endpoints meeting on the same side, well, two lines with the same endpoints and the same lengths. Meeting on the same side, but at a different point. Same side is in the same side of AB, but at a different point. Okay, so I guess the construction here is that suppose you have another two lines that are, you know, here. I should have used the other tool. Now I have to erase it. Hopefully this is not too... Let's just redo this line. Right, so yeah, suppose we have another thing here, right, same lengths, then these are necessarily different points. And so what we're going to do is, of course, we're going to, like we usually do, try to construct it and then derive for us a contradiction. And join up C and D here as well. Okay. Okay, so what we're going to do. So proof. So let AB be a line. Assume AC and BC are equal to AD and BD. So we're going to assume... let's write the whole thing out. Why not? Slightly wary of the room that I have left, but I think we're okay. So let AB be a line, as shown, right? And assume AC and BC are equal to AD and DB, or AD and BD, respectively. AD and BD, respectively. I just wrote DD, which is not what I meant to write. BD, respectively, right? So also assume that C and D are on the same side. So also assume C and D are on the same side of AB. Okay, so now we can draw some conclusions. Since AC is equal to AD, right? So AC and AD are equal by assumption, right? They're one of the pairs of lines which are supposed to be equal. I'm going to mark them in here, AC and AD, right? So now we have an isosceles triangle there, so we can conclude that the base angles of this triangle are also equal, right? And then the base angles ACD and angle ADC are equal. And we've met this proposition in proposition 1.5, right? And so therefore, thus, angle ADC is greater than angle ACD is greater than angle ADC. So ACD, angle ADC, right? So ACD is the big angle here. I'll just mark it in, right? And it's greater than ADC because it's, because ADC, wait, what have I written here? Sorry, my mistake. So what I want to say is that ACD, the larger angle, right, is actually greater than DCB, right? So DCB is this small one here, and of course it's greater than that because DCB is part of the greater angle, and DCDB is much greater than DCB. So I'm going to go and use inequalities now to make this clear. So CDB is greater than ADC is greater than DCB, right? So this is what we've just said, right? CDB is this angle here, right? It's greater than ADC. It's greater than ADC, right? Because it's part of, this is the tiny angle that is part of the bigger angle, and that's greater than DCB from what we've just said earlier. So I think I'm unable to keep this in the same board, so let's drag over to the next board and finish the last statement there. Okay, so so what have we concluded? Well, let's just write that bit again, right? So we've concluded that angle CDB is greater than angle DC is greater than angle DCB. So now to finish off the argument, we're gonna use the other two sides that we assumed were equal, right? So since CB is equal to DB, right, we have angle CDB equals angle DCB, which is impossible because it contradicts the inequality that we've just written down, right? CDB is supposed to be much greater than DCB, but then we've also shown that if we assume these pairs of lines originate from A and B are equal, then these two angles are supposed to be equal, right? So this is impossible, and so therefore the premise that C and D are distinct points is also false. Cool, any questions? So I think we may be able to finish off one more. The next one is pretty short. I think for the most part, we've seen this before several weeks ago. So let's push on and try and get one more in. This is proposition 1.9. And this is about bisecting an angle. So I think bisecting an angle is, this is actually pretty neat and super simple to explain. A little bit simpler than the last one, right? So what we want to do is we want to cut a rectilinear angle in half. Okay, so I'm going back and using Euclid's, well, the translated statement anyway, because this is relatively clear what we're trying to do. So let's draw the picture, right? So we have an angle, BCA, right? So this is an angle, and we want to cut in half. So BCA, BAC, sorry, BAC. So I want to cut this in half, or bisect the angle, as we like to say in modern terminology. So we want to construct something on this so that we can cut it in half using some of the constructions we had before. So the construction is that you let D be a point on AB. I guess this is one of the things that Dan complained about, that sampling a point randomly on a line, you know, what does that even mean? But I guess, you know, if you think of a line being consisting of points, then just pick one, right? So, right, so let D be a point here, right? And we want to let E be a point on AC such that AD is equal to DAE. So this is something that we've done many times before. We want to construct it like this. Let's draw this in, right? So, and so I want to let E be a point, writing too fast, be a point on AE such that AD is equal to AE. I believe this is proposition 1.3. Seen this a few times in the past now. Common trick that Euclid likes to use. And so now the next construction is that we want to also construct an equilateral triangle with base DE. So construct equilateral triangle. I guess I'll just call it DEF. I guess all sides of a equilateral triangle are equal citizens, so we don't really need to say it's the base, right? It's just one of the sides, and we're just going to stick the triangle here. There are two ways it can go, but it doesn't really matter which way. We can put it below to make the diagram a little bit easier to read, or just easier to parse. So here's an equilateral triangle, DEF. And we're going to just join up A and F. And that actually worked. And the claim is that the line AF bisects the angle BAC, or in other words, the angle BAF is equal to CAF, right? So here we go. So the claim, so we're going to join up A and F, right? Again, I'll leave that out as one of the applications of the postulates of the claim. No, that didn't work. So the claim is that angle BAF is equal to angle CAF. Right, so proof. So this is really just an observation that we've got two congruent triangles with, well, you're gonna know which triangles look at. It's these, the triangles ADF and AEF, right? So once you show that they're the same triangles, then you're good, right? One of the matching angles, BAF will be equal to CAF. Okay, so we're almost done. So since AD is equal to AE, I'm gonna go back to using equals notation. We've kind of just written them out above. So this is by construction, right? We've constructed the point E such that these are the same. AF is common, right? If we're looking at the two big triangles on the screen, ADF and AEF, right, then AF is a common side. And DF and EF are the same, right? And DF is equal to EF because equilateral triangles. Maybe this is not going to fit. Try the equilateral triangles, right? And so by proposition 1.8, the claim follows, right? So claim follows from proposition 1.8, which I assume must be the one that says that if you have a triangle with three matching sides equal, then all the corresponding angles must also be equal as well, and therefore BAF is equal to CAF, therefore AF bisects or cuts the rectilinear angle CAB in half. Wow, I never seem to be able to get this tool right, but that's it. That's it. Cool. Right, so I think that's probably all we have time for today. Yeah, you guys got any questions?